Welcome to this explainer. Today, we're putting on our quantitative detective hats to uncover the mathematical truth hidden inside financial data. We'll be exploring Learning Module 9 from the Quantitative Methods curriculum. Basically, we're going to unpack the exact mathematical tests analysts use to prove whether two sets of data are actually related to one another, or, if they're just playing tricks on our eyes.
Okay, let's quickly glance at our roadmap for today. We'll be sequentially unlocking 3 major statistical tools to figure out if variables are connected. First, the Pearson t-test, then the Spearman rank correlation, and finally, the chi-square test for categorical data. Section 1, Proving Relationships in Data. Let's get right into it. So as lead investigators, our core problem is that data often lies to us. It can look completely connected when it's really just pure chance. Whenever we look at the markets, we have to constantly ask ourselves, are these data points sharing a meaningful relationship, or are they literally just bouncing around randomly? A significance test of a correlation coefficient is exactly what allows us to confidently assess whether that relationship is mathematically real, something we can actually use for forecasting, or if it's just a total fluke. Now get this. Consider the absurd 0.824 correlation coefficient you'd find if you compared monthly U.S. retail sales of beer, wine, and liquor against atmospheric carbon dioxide levels from the years 2000 to 2018. I mean, an R.824 indicates a massive positive relationship, but obviously there's absolutely no underlying reason that atmospheric CO2 is being driven by retail liquor sales. This is a perfect example of a spurious correlation. The math looks incredibly strong on the surface, but the reality is pure coincidence. We need rigorous tools to separate the signal from the noise. That brings us to Section 2, Parametric Tests, specifically the Pearson correlation. To separate fact from fiction, let's open up our toolkit to our very first and honestly most standard analytical tool. When mapping out the annual returns of Investment 1 and Investment 2 over a 33-year period, you might intuitively feel they move together somewhat. But feelings aren't facts, right? We need a formal t-test to mathematically prove that relationship isn't just a visual trick of the eye. This specific tool, the parametric t-test, relies on some pretty strict parameters. It's designed specifically for data that is normally distributed and continuous, meaning numerical data without wild extreme outliers. To prove a correlation is significantly different from zero, we calculate a t-statistic using n minus 2 degrees of freedom, where n is just our sample size. And here's an interesting quirk. As your sample size gets larger, the magnitude of the correlation needed to reject the null hypothesis actually decreases. By calculating these t-statistics across a matrix of mutual funds, we can rigorously prove which fund returns are significantly correlated. For instance, against a critical value of plus or minus 2.032, most funds in a typical matrix might show significant correlations. But if we find a relationship, let's say between a Fund 3 and a Fund 4, where their calculated t-statistic is only 1.903, well, it falls short. It fails the test. We simply cannot confidently say those two funds are correlated. But what happens when our data just refuses to fit those neat, continuous bell curve requirements of a parametric test? Well, we have to shift gears to non-parametric tests. These are our flexible tools. They make minimal assumptions about the underlying population distribution, which is absolutely crucial for handling the messy, skewed, or categorical data we constantly face in the real world. Section 3, Handling Skew with the Spearman rank correlation. Let's see how we deal with the messy stuff. When our data is heavily skewed or packed with wild outliers, our standard parametric t-test just completely breaks down. We need a much more rugged tool. Enter the Spearman rank correlation. Instead of testing the raw numbers, which could be massively distorted by just one crazy outlier, the Spearman test looks at the relative positions of the data. By converting raw values into ranks, we completely mute the impact of those extreme outliers. Okay, let's dive into this incredibly simple 3-step recipe. It essentially applies the standard correlation logic, but replaces chaotic raw data with a cleanly ranked order. First up, you rank your observations from largest to smallest for both variables. Oh, and a fun little rule here. If two values happen to be tied, you just assign them the average of the ranks they jointly occupy. Second, you calculate the squared difference between the ranks for each pair. And finally, you just plug those squared differences right into the Spearman formula. Let's see this non-parametric technique in action. Imagine we're evaluating mutual fund alphas and expense ratios.
The raw alphas might all be negative, maybe ranging from negative 0.13 all the way down to negative 1.01. By converting these messy raw numbers into clean ranks, say 1 through 9, and comparing them against the ranks of the expense ratios, we can suddenly uncover hidden relationships. It completely shields our analysis from non-normal distributions, letting us run a reliable t-test on the ranks themselves to see if alpha and expense ratios actually move together. And that brings us to Section 4, categorical data, contingency tables, and the chi-square test. Up until now, we've only dealt with numbers. But what do we do when our investigation involves classifications? Like evaluating ESG ratings as progressive or poor, or grouping ETFs into value or growth. This forces us to shift gears completely. Think about it. You literally cannot calculate a numerical mean or a variance for the word growth or the category progressive. It's text, it's discrete. So instead of testing for linear correlation, we must test for independence. We want to know, does being in category A affect your chances of being in category B? We solve this puzzle by building what's called a contingency table. Let's say we're looking at different ESG dimensions, environmental ratings versus governance ratings. First, we take our total sample and calculate the exact frequencies we would expect to see in every single cell if the two categorical variables were completely independent of one another. This expected grid essentially acts as our baseline of pure randomness. To find our answer, we bring in the chi-square test statistic. The formula is actually quite elegant. It's simply the sum of the squared differences between what we actually observe in the real world versus what our baseline table expected, scaled by that expected frequency. This test uses degrees of freedom equal to the number of rows minus 1 multiplied by the number of columns minus 1. If our observed data exactly matches our expected data, well, the chi-square statistic is just 0. But the larger the difference, the larger that positive chi-square number grows. When we map out the residuals, the differences between those observed and expected frequencies for, say, ETF sizes and investment styles, the results can be striking. Imagine deep blue areas showing there are way more medium-sized growth ETFs than expected by pure chance. Then, deep red areas showing there are far fewer large-sized growth ETFs than expected. Because these differences are so massive, our chi-square statistic would blow right past the critical value, forcing us to reject the null hypothesis. Boom! We have mathematical proof that ETF size and investment type are highly dependent on one another. So as statistical detectives, your toolkit is now complete. You have the Pearson t-test for evaluating linear relationships in neat, normal, continuous data. You have the Spearman rank correlation to cut through the noise of heavily skewed data and massive outliers. And finally, you have the chi-square test to evaluate the independence of discrete, categorical classifications. You literally have a precise mathematical method for any type of data you might encounter out there in the field. But before we wrap up today, always remember the golden rule of quantitative analysis. Correlation does not imply causation, simply association. These tools are incredibly powerful for proving that variables move together, but they cannot tell you why. Whether it's mutual fund alphas or, retail liquor sales and carbon dioxide, the math only points out the pattern. It's up to you as the analyst to determine if the logic actually holds up. Knowing how to mathematically prove correlation and independence is a foundational skill in finance. It's what takes you from just guessing based on a chart to knowing based on rigorous mathematical proof. Thanks for joining me in this explainer, and I hope this leaves you excited to go test the independence of the very next data set you get your hands on. Catch you next time.